Okay, today we're doing gravity, Newton's universal law of gravity. Newton's universal law of gravity. So I'll be working through some of the problems we did in class. These problems are on the lecture slides, so you can work through them, try them yourself. If you can't get through them, then come back and check here, and you'll see the solutions. So let's look at this first example. Two identical spheres that weigh 100 newtons each sit on the surface of the Earth 10 meters apart. What are the magnitudes of the gravitational forces A on the spheres from the Earth and B on the spheres from each other? So let's just draw a sketch of the situation. So this is the surface of the Earth. This is sphere 1. This is sphere 2. I'll say Fg1 equals 100 newtons. That's the weight of the sphere on the Earth. And we have Fg2, which is equal to Fg1, which is equal to 100 newtons because they are identical spheres. We also know that the distance center to center R equals 10 meters. And remember, when we're talking about gravity, we're always talking about center to center, the center of one object to the center of the other, which is not usually a big deal until we start dealing with planets and moons and that kind of stuff. With huge radii, you have to factor that in. Okay, and Fg1 equals Fg2 equals 100 newtons. And we know this is the weight on Earth. Okay, so if I were to draw free body diagrams of these two spheres, you would have Fg. I'm just going to drop the subscript, call it Fg, because Fg1 and Fg2 are the same. And we have the force on object 1 from object 2. That's how I'll label it, F21. That is the gravitational force that this object feels as a result of this object's presence. It's being pulled to the right because the two attract each other. Likewise, over here I have the force F21. That is the gravitational force on object 2 from object 1. Okay? So this is our free body diagram. We also have the normal force to be complete because it's sitting on the surface of the Earth. Okay, so part A asks, what is the gravitational force on the spheres from Earth? Well, we already know that because we know Fg. Fg equals 100 newtons. That is the weight of the object on the Earth's surface. So that means that is the pull on the object from Earth. Simple as that. And they're both equal because they're identical spheres. So that part was fairly easy. And we also know Fg equals mg because we're on the surface of the Earth. So the force of gravity on the surface of the Earth is always mass times the acceleration of gravity, which applies only on the surface of the Earth. I know I said that like 3 times. I'm trying to get my point across. So part B says, what's the gravitational force on spheres from each other? Okay, so what they're asking here is they're asking this F12 and this F21. They want to know what gravitational force does this object 1 feel from object 2. So we're ignoring the force of gravity from the Earth. We don't care about that anymore because the question is just asking what is the gravitational force that they feel from the presence of the other gravitational force. Well, remember how we said the force of gravity on the Earth's surface is equal to mg? Well, that's not going to apply here because, yes, it is on the surface of the Earth, but this only tells us what the force of gravity from Earth on the surface of the Earth is. But here, we want to know what the force of gravity from some other object on the surface of the Earth is. So if you're ever dealing with a case that involves gravity and you're not talking about the gravity from Earth on the surface of the Earth, then you cannot use this Fg equals mg, because this is just an approximation. Only applies to force from Earth on Earth's surface. So what we have to do instead is use Newton's law of universal gravity. I'll give it a subscript capital G, which is m1 m2 over r squared. This is universal. Applies everywhere. It's very important. This formulation of gravity applies to applies on the Earth's surface, on the surface of the moon, in between the Earth and the moon, in the middle of the Andromeda galaxy, wherever. This is a universal law of nature. This is Newton's law of universal gravity. Now, there is another formulation of gravity that involves general relativity. There are other ideas of gravity, like quantized gravity and all this other crazy stuff that we're not going to come near. But in the world of Newtonian physics, which is all we're going to touch here, this is a universal law that applies everywhere. Okay. And in all situations where gravity is considered. Okay, so what in this case it would be the magnitude of F12 equals the magnitude of, well, I'll actually just draw a vector bar and magnitude signs. F21 equals G m1 m2 over r squared. So back to our drawing here. This F21 is equal in magnitude to F21, opposite in direction. But their magnitudes are equal, and the magnitudes are given by this. Okay, so now it's just a matter of, oops, we don't have mass. Uh-oh, how are we going to find the mass there to plug in? Well, we know Fg1 equals 100 newtons, and we know this equals mg only because we're on the surface of the Earth when we're weighing this. So weighed on E's surface. So then, we can say the mass, well, let me put subscript 1 there. Mass 1 equals Fg1 over the acceleration of gravity g. Again, let me sum up why we could do this. This 100 newtons is the weight of the sphere on the Earth's surface. So we know that equals m1 times g, little g, because little g applies to the gravitational force on Earth's surface. So if we take this Fg1, which is variable, you move to another planet, you move to the moon, this Fg1 is going to change, but g, the acceleration of gravity, is applicable on the Earth's surface, and this is the weight on the Earth's surface, so these two give the mass, and the mass is universal everywhere. Mass is just mass. It's like a meter. A meter is the same here as it is on the moon. The mass is the same here as it is on the moon. Okay. And we also know that m2 equals Fg2 over g, because it's the same thing. And I can even just put equals m1. So I'll insert that here, capital G times Fg1 over g times Fg2 over g over r squared. So this equals g times Fg1 over g times Fg1 over g, because Fg is the same as F2, so I can just put that in there twice for r squared, equals g times Fg1 over g squared, because it's times itself, so it's squared, over r squared. Okay, so if I then continue F1, 2, and again I'm dropping the vector bars because we're talking about magnitudes, equals g times Fg1 squared over g squared r squared. I just moved things around a little bit, made it a little cleaner. And let's see. I have that calculated somewhere. Yes, I do. So this equals 6.67 times 10 to the negative 11th times newtons meter squared per kilograms squared. This is a constant of nature. This is just it's like pi. You know, what is the ratio of the diameter to the circumference of the circle, of any circle? It's pi. It's pi here, it's pi on the moon, it's pi all over the universe. It's just like it's a constant of nature, and so is this. Times 100 newtons squared over 9.8 meters per second squared, squared times 12 meters, was it 12? 10 meters, excuse me. If we multiply all that out, we get F12 equals 69.5 times 10 to the negative 12 newtons. That's our answer. Again, that's a positive force over here, and over here that's the magnitude of the negative force. But we're just working in magnitudes. So let's look at the next example. On Earth, we have two parts of a space probe that weigh 11,000 newtons and 3,400 newtons. These parts are separated by a center distance of 12 meters and may be treated as uniform spherical objects. Find the magnitude of the gravitational force that each part exerts on the other out in space, far away from any other objects. Well, I'll draw my on Earth situation. R equals 12 meters, and we have F1, I guess we can call it F1G, that's the weight, first one. F2G, 1G equals 11 newtons, and F2G equals 3,400 newtons. We also have this force, just like before, we have the force 1, 2, and the force 2, 1. So that is the situation on Earth. This is on Earth. So in space, the situation is going to look like this, with R being the same thing. Oh, I'm sorry, I forgot that you have the normal force too. F21, and now there's no gravitation, there's no F little g, because there's no Earth pulling down on it. It's just these two objects are pulling on each other in space. So it's just the gravitational force. Now this is just like the problem before, where we want to use Newton's law of universal gravitation because we are not on Earth's surface, m1, m2 over r squared. Again, we don't have the mass, but we can go back here to the on Earth example and say, well, this is the force of gravity on Earth's surface, so that equals mg, m2g, and m1g. So therefore, m1 equals f1g over g, and m2 equals f2g over g. I can plug those in because if you find the mass on Earth, that mass is going to be the same in space because mass is a constant thing. It doesn't depend on where you are. The weight does depend on where you are. Equals g times f1 over g times f2 over g over r squared, where r is 12 meters. Okay, don't get the little g and the capital G mixed up, just by the way. So g equals f1 f2 over g squared r squared, or 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared times f1 11,000 newtons times f2 3,400 newtons over 9.8 meters per second squared times 12 meters squared. Fg equals, got this somewhere, (180 times 10 to the negative 9th newtons). So the question is asking us, find the magnitude of the gravitational force that each part exerts on the other in outer space far from other objects. Well, that is this. Now, you do know that here it's positive 180 times 10 to the negative 9th. Oops, excuse me. Here it's positive, but here it's going to be a negative 180 times 10 to the negative 9th. Okay, moving on. Synchronous communication satellites are placed in circular orbit. Placed in a circular orbit that is 3.59 times 10 to the 7th meters above the surface of the Earth. What is the magnitude of the acceleration due to the gravity at this distance? Okay. I want to draw my picture here. And this is my satellite. Call this RS. And here's the trick here to this problem. When we use Newton's law of universal gravitation over r squared, that's your general law. So start with this first. Now, as I start thinking, okay, so I've got M1 is, oh, I don't have M1, and M2 is just mass of the Earth. Or M1 could be mass of the Earth and M2 could be the satellite. It doesn't matter. So what is R? Well, that's the question, because R is the separation from the center of this point to the center of this point. So that means I'm going to have to take the radius of the Earth into account. I'll use capital E. So the radius here, the separation between the two objects from which the gravitational interaction is occurring, is the radius of the satellite plus the radius of the Earth. So now I will, well, we're asked for what is the acceleration of gravity. We don't know, because we know the acceleration of gravity right here is g, but right here, that's far away from the Earth's surface, so we don't know what that is. To better picture this, let's look at the free body diagram of the satellite. You'll have the force of gravity, and, well, that's it. That's the only force you have. That's the free body diagram, X and Y. So if you sum up the forces in the Y direction, you just have the force of gravity. And that equals mass times the acceleration, the Y direction I drew here. Because Newton's second law says that. Okay, so is there a net force? Well, yes, there is, and we find out later with centripetal acceleration and centripetal force. The force anytime something is moving in a circle, even with constant velocity, it's still accelerating. So it's still going to have a net force called the centripetal force. But you can also think of that as just there's no other force acting on this. So that's the only force there, so it has to be the net force. So the force of gravity equals mass times acceleration. And we know the force of gravity is g m1 m2 over r squared. Again, that equals mass times acceleration. What is being accelerated here? Well, if we look at the force onto AY, not A2. If we look at the force onto the satellite, we're talking about the acceleration of the satellite. We could also look at the acceleration of the Earth, but the Earth is not going to accelerate much because it's so massive. But right now, we're just looking at the forces on the satellite, so that's M1 and M1. Well, immediately you see M1 and M1 cancel, so g m2 over r squared equals a2. Or in other words, g times the mass of the Earth over r squared is equal to the acceleration of gravity. We're using the mass of the Earth. If we were using the radius of the Earth, that would just equal to be 9.8 meters per second squared, but it's not in this case because I'm flipping the equation. G times mass of the Earth over rs plus re squared. So that extra radius of the satellite here, which is this distance above the Earth's surface, that causes this to not be 9.8 meters per second. So acceleration of gravity is 6.67 times 10 to the negative 11th newtons meter squared per kilograms squared times mass of the Earth, which is actually given to you over here in the problem. It would be in a chart or given to you in the problem in any situation. So that is 5.972 times 10 to the 24th kilograms over radius of the Earth, 6.37 times 10 to the 6 meters, plus the radius of the distance of the satellite above the Earth, which is 3.59 times 10 to the 7th meters, all of that squared. And if you calculate it out, acceleration of gravity is 0.223 meters per second squared, which is not equal to 9.8 meters per second squared. Okay. All right, I'm going to stop here because now we're done with gravitation, so I'll move on to the spring force in another video.